A logarithmic equation would be one that has a log in it that we are trying to solve for wherever the x is. We're going to work on solving logarithmic equations in this video. We have a couple of techniques, so let's talk through them. First one, example here, says log base 4 of x equals 3. When I see a single log equal to a constant, my instinct is to just use the definition of a log. So remember, we kind of make our loop here. 4 to the third is equal to x. That means x is what? 16 times 4 is 64. So that's how we solve something like that. Here's another one. Make our loop. X squared equals 4. Solving that, we would get x equals plus or minus 2. However, our base cannot be negative. So our only answer here is x equals 2. Log base 2 of 4 would equal 2. Similarly here, our base is e to the third will equal 2x minus 6. Add 6 to both sides. Divide by 2 or multiply by 1/2, however you want to write it. You could write it like this, or of course, x equals e to the third plus 6 over 2. Okay? Suppose you could distribute that into any of these three is an appropriate correct value for x. Let's take a look at the next example. One thing we do really have to be careful of, just like up here, we had to double check these and say, we can't have x equal -2 because our base can't be negative. We do also need to make sure that we don't have a negative inside the log. So for example, here it would not be appropriate if we got a negative number for that x. Here, the number itself could be negative. It's just when you plug it in, you can't get a negative. Here, when we get this, we are not going to get a negative inside of there. We're going to get e to the third, because the natural log of e to the third is 3. All right. This one is a little different because it has 2 logs in it. And specifically in this case, it has 2 logs with the same base on opposite sides of the equal sign. That takes me back to this property that we had, that we saw in the last video. This guy right here. If you have 2 logs equal to each other with the same base, then the insides are equal. That's called the 1-to-1 property of logs. We are going to use that for this example, where we have 2 logs equal to each other with the same base. The only way for that to happen is if the insides are equal. Subtract x from both sides. Add 2 to both sides to get the variables on one side. You have 2x equals 3. Divide by 2, you get x equals 3/2. I just do a quick mental check up there to make sure that I don't get any negatives inside either of my logs. The right-hand side is clearly okay. You get 5/2. The left-hand side, you get what? 9/2 minus 2. Still positive. It's okay. Let's try this one. This is a little different than the previous one because I don't have a single log on each side of the equal sign equal to each other. This is where my property, where I can condense the logs, comes into play. The left-hand side of this can be rewritten as log base 2 of x minus 2 times x minus 3. The right-hand side of that, if you wanted, you could make that 1. Log base 2 of 2 is 1. Or, now that we have a single log equal to a single log, we can just say the insides of the logs must be equal. This is not 0 on the right-hand side. So we have to distribute out the right-hand side, subtract 2 from both sides, and get our solution that way. Factor. That gives me x equals 4 and x equals 1. And I have to ask myself, are both of those solutions? The answer here is no. X equals 1 cannot be a solution because it makes that have a negative inside the log and this one. So that cannot be a solution. You must go back to the original and check and make sure that it's part of the domain. I guess you could, from the beginning up here, we could say x has to be greater than 3, right? Because this one requires x greater than 3 and this one requires x greater than 2. The combination of those, the smaller set there, the intersection of those is that. So x has to be greater than 3. And so the only solution that fits in that is this guy. X equals 4 is our only solution to that. Remember when we had this problem where we had 2,000 bacteria present and we wanted to know when? We came up with this equation. 2,000 equals 200 e to the t. And we divided by 200. And we got 10 equals e to the t, and we did some guess and check, right? Just plugging numbers in for t and to see how close we could get. Well, now we have a technique for solving this. This is an exponential function because we have a variable in the exponent. So I'm going to take the natural log of both sides of this equation. Natural log of 10. Natural log of e to the t is just t from that property that we had where it was the log base a of a to the n was equal to n. I think I used different letters, I don't remember, but that exponential and logarithmic function simplify one, cancel one another out. So this is just t. So t is the natural log of 10. That would be the exact value that would make this true. And throwing that in our calculator, natural log of 10 gives us that approximation of 2.3 that we got from guess and check. But this was a whole lot quicker, right? And we have an exact answer too. All right, that's it for solving logarithmic equations in this video. Next, we want to get into exponential growth and decay. This is modeling real-life applications of exponential growth and decay. So we will see that in our next video, kind of wrapping up our study of exponential and logarithmic functions.